All right, so just to reset the problem here, the first thing I need to do is just for a particular student who's watching this now in the room, niner, niner, niner. There you go. Breaker 1 niner. I threw that in there as a bonus. But on this video, what we're showing here is the finishing of a sample problem that we started in class. This has to do with, I put a block on top of another block, block on top of another block, and in those two things, there's a coefficient of friction between these two that I'm calling mu static 1. And I'm concerned with the static coefficients of friction because in the directions of this problem, I want to make M1 stay at rest relative to M2. I want to figure out how much mass I can make M3 have and yet still have the condition of M1 is at rest relative to M2 be in place. So M2 is going to accelerate up this ramp, but M1 is going to stay on top of it and accelerate with it. Okay, so we did some background work yesterday with this where we drew free body diagrams for each block. That's what we've got shown in these pictures. So we drew the free body diagram for block 1, and we just had normal force, which is the force that block 2 exerts on 1. We had friction acting this way, and we were clever in figuring out that friction was going to push this thing forward because gravity is going to have this block, if we broke gravity into components, let's go ahead and do that. Gravity would have a parallel component and a perpendicular component. That parallel component would be trying to make this block slide downhill. So we're assuming that there's significant friction and significant static friction such that this force of friction can not only balance this, but have enough left over to make it accelerate upward. Okay, then we looked at block 2, and since we're looking at these as isolated objects right now, we have the same force of friction. It's retarding the motion of M2. We have friction on its base, and then we had a gravity component that we had to overcome, and we have tension that's yanking this thing forward. And then our final piece was we had tension and gravity acting on this one, and gravity is going to be bigger than tension because it's got to make it fall down. Okay, we went ahead and applied Newton's second law, net force equals ma, to block M3, and just looked and said, look, our goal is to figure out how big M3 can be. So in this expression, we need our answer to be in terms of g, a, theta, the masses, and the mu's. This basically says if we can find that tension, we're done. So that's why we went from that block and started to mess around with the two individual blocks. Okay. If you're sitting there at home watching this, the next question I would ask is, so which block do you go to next? So think about it for a second. Which block would you go to next? I'm giving you time to puzzle, or you can just push pause if you need more time to puzzle. Okay. And then someone from our audience is going to say, M1 seems like an excellent choice. I think so too. And the reason, our live studio audience, the reason that M1 is a good choice is because M1 is the block that has a limit to how much force it can have up the ramp. This tension, our ropes are ideal. They're not going to tear in half, so you can put as much tension as you want to, 12 billion newtons if you want to, and that rope's just going to yank that block off the ramp, basically. But this friction force is constrained by the coefficient of friction between M1 and M2. It can only be so big. And if you exceed this amount of friction force, if you need more than that friction force to make this thing accelerate, well then M1 is going to slide off of M2. Okay, so check and make sure that that makes sense in your head. Okay. Yep. So then what we need to do is start to look at that block. Okay, so let's apply net force equals ma in the parallel direction and in the perpendicular direction to that block. So in the parallel direction, and we may eventually need an extra screen, I always like to label my work so that I know what work goes with each direction. So I write out parallel direction. I've had people ask me, what is the 11 direction? Don't ask that question. That's just not a good question. So in the parallel direction, I'm going to apply net force on M1. So it's net force equals M1 times A, because we're doing free body diagrams for each individual object. Okay, in that free body diagram, this block is going to accelerate in that direction. And so the system we use, the convention we use in here is we always take the forces in the direction of acceleration minus the forces opposing that acceleration. So we're going to say that force of friction static, minus force parallel is going to give us M1 times A. And remember that we want our system to all move as one, So this A is not a variable. This A is a given, and it's the same for all 3 blocks. Because it's just the magnitude of A. I don't have a vector symbol over that. Okay, well my force of friction can further be broken down. It's going to be mu static times normal force. If I'm looking for how big I can make M3, then what I want to do is maximize the amount of friction on M1. I'm saying, look, if I'm absolutely just going to see how fast I can make this go, well, then I want this force of friction that's propelling it forward to be as big as I can get it. Well, that happens when I'm maxing out my static friction. So that's why I'm using mu static times normal force, because that static friction size can vary, but if I'm looking for the absolute maximum friction I can get, this is it. Okay, minus force parallel, which is m1g sine of theta, equals m1 times A. Okay. All right. I made this substitution. I probably should keep on going with it, because normal force is not allowed to be in my solution at the end. So I got to find a way to eliminate normal force. Well, if I'm looking at my free body diagram, if you want to be really formal, you can write out that this force perpendicular, which is m1g cosine of theta, it has to be equal to that normal force. And so you can prove that in the perpendicular direction. We're going to be so good at this that I'm okay with you just looking at this and eyeballing it and say, look, those two are equal in size. So then this will say that mu static times m1g cosine of theta minus m1g sine of theta is equal to m1 times A. Okay. All right. Our next step. My goal was to eliminate tension. I have not eliminated tension. I have not even had tension show up in this equation yet. So while this is a good choice, it hasn't gotten me what I need. So I probably need to go to block 2. And I probably need to move this thing out of the way. It was a big day the day I realized you could move that while you were filming. Alright, so on to mass 2. On mass 2, in the parallel direction, I'll kind of draw a little squiggly dividing line around my work there. I want to apply net force equals m2 times A. Okay, and then I need to do some solving. So, or some net force equals ma stuff. So on that block, I'm looking at the parallel direction. It looks like I have tension causing the block to accelerate in that direction, minus force of friction 1, because it's opposing, minus force of friction 2, minus force parallel on block 2, and that equals m2 times A. Because I have both frictions and force parallel all opposing my motion. Okay. I can go ahead and plug some stuff in. Really what I need to do is solve this for tension. So tension is equal to m2A plus force of friction static from block 1 plus force of friction from block 2. Yes. For block 2. Excellent point. You just, Baron von Segway, you just borrowed my question. Somebody in our audience just asked a question, are we using kinetic friction for block 2? You betcha. Because block 2 is sliding because the system is accelerating. But static friction between 1. So this, we might want to remind ourselves, is kinetic. Minus force parallel 2, or sorry, plus force parallel 2. I got lost to where I was. And I think that's it. Yep. So now it's just a matter of plugging everything in. That tension is going to equal m2A. Well, that's in terms of things we already are allowed to use. It's in the m's and the A that we were given. Force of friction static 1, which we actually could probably just plug in from here. Force of friction static is going to equal m1a plus force parallel on block 1, plus force of friction 2, which we can calculate, and which we're going to calculate, plus force parallel 2, which is pretty easy to do. Okay, so let's start writing that out in all these little terms. It's going to be a very convoluted solution at the end, but if each piece makes sense, we'll be okay. So tension equals m2a, that's the easy term. Force of static friction is going to equal, I'll do this in a bracket, m1a, I'm just looking at this equation here, plus force parallel on that block, which is m1g sine theta. Okay, that was all our force of static friction on block 1, plus our force of kinetic friction. Okay, so our force of kinetic friction is mu times the normal force on that block, plus force parallel 2, which is m2g sine of theta. Okay. And then I'm getting closer and closer and closer to having this in only the variables I need. But this normal force 2 is still a bit of a problem. How big is normal force 2? Okay, so this normal force 2, if I'm looking at the free body diagram I drew for block 2, that normal force has to balance out all the other perpendicular forces, because this block is not accelerating off the ramp or through the ramp. So that normal force 2 has to equal this force of 1 on 2, which is just this thing, which we already found was m1g cosine of theta. And it has to equal this perpendicular component, which is m2g cosine of theta. So it has to equal the sum of those two. This normal force has to balance out this, and it has to balance out that, which equals this. So my next statement is tension equals m2a plus that whole mess, m1a plus m1g sine theta plus mu kinetic 2. I should be specific about what mu I'm using. Mu kinetic 2 times m1g cosine theta plus m2g cosine theta. That's that normal force, plus m2g sine theta. Okay? That whole expression, that whole ugly thing, that's the tension that you're going to have. And then you're just going to take that tension, plug it in here, and that solves for how big that M3 needs to be. Okay. Okay. Now, if you're looking at this, a question that I anticipate you might be asking in your head is, look, I see M2A and M1A, so that's the acceleration of that part of the system. I see an M1G sine theta, I see an M2G sine theta, and I see this whole big friction term that really is just the kinetic friction with the other block. Yes? Yes. Ooh. Yes. Because this is the static friction piece from the other block. Well, if I look at this, static friction and the static friction coefficient didn't actually come into play here, as in it didn't show up in our equation, because I didn't ask what value this mu must be. A different version of this problem would say, figure out what this mu needs to be in order to make this work. But what this does say, this is actually just the net force, or like what the tension must be if you solve this as one system with M3 and M1 and 2 as one object. You've got the gravity resisting term, M1g plus M2g times the sine of theta. You've got the acceleration of both those, m1 plus m2a, so you're acting like they're accelerating as one mass. And you've got the static friction. There's nothing that is internal to the system. You've got the kinetic friction term, sorry about that. There's nothing in there that's internal to it that comes from the static friction, because if I use m1 and m2, static friction is internal to those two as a system. But that's what came out of this piece, is that internal piece spells out in the static friction part. So as our final step, again, you're just going to take that tension expression, this whole big long thing, you're going to plug it in up here for tension, and then that long, nasty algebraic expression is your answer for what M3 can be. So that ends this one.